Hi, and welcome to this video where we'll talk about solving problems using dimensional analysis. And the whole reason for this is that if you're studying chemistry, there's really two things that we're concerned about when we see a number, right? We want to think about, first off, the value of a particular thing, and second off, the units. So, for example, imagine that I said, I'd like you to do some job for me, and I'm going to pay you 140. You're really pretty interested in whether I told you 140 and I meant $140, right? Versus 140 cents, right? You're much more likely to work for me under one scenario versus the other. And just like that in chemistry, I care, right? If I'm talking about 50, what do I care about? Whether is it 50 atoms of a particular element? Is it 50 moles of atoms of a particular element? And we'll get to what those units mean later. But I care. It's more than numbers. It's what those units are. And so if I want to solve problems, then what I have to do is I have to track units. If I don't pay attention to the units and I end up talking about a different unit than what the problem wanted, I'm going to end up getting it wrong. And so I track units in order to avoid that. So here's a few simple examples, and I'm going to be using what we call dimensional analysis or unit analysis. You may have seen this in a previous course in high school, for example. It's my preferred way of keeping track of this, but I would strongly suggest using a method like this. If you don't keep the units in your problems, you're going to have a very hard time. So get used to using a strategy like you're going to see in this video. So we'll start with a really simple example of just simple dimensional analysis unit conversion. And the question is, how much money in dollars and cents do you have if you have 1,579 quarters? And you know as well as I do that there's 4 quarters in a dollar, so you just divide by 4 and you'd work your way through from there. That's a conversion factor that you always have in your head, and so it's an easy one to do. What I want to do, though, is show you how to do dimensional analysis with this problem so that you can use it in future scenarios. And so all we're going to do is track all those units and go through, because this will be useful in scenarios where you don't have that unit analysis idea or a mental equation or algorithm right at your fingertips. So we'll start with those 1,579 quarters. And again, you know that you would instinctively divide by 4 to do this, but let's show you how this works, right? Our goal is to turn quarters into dollars and cents. And so we know that if we take a quarter and a dollar, we can build a conversion factor. We can watch the units go from one thing to another thing. And we already said that there's 4 quarters in $1. And so you see where the divide by 4 is, right? That on the top of the line are things that I would multiply together, and on the bottom of the line are things that I would divide by. And so what I'm left with is 394.75. That's what happens if I take 1579 divided by 4. Let's look at what happened to our units. I see quarters on the top of the line, and I see quarters on the bottom of the line. That's a good thing in this case because we didn't want to have quarters anymore. We wanted to be in dollars and cents. The problem was asking for a different unit, so we better hope that this quarters goes away at the end. So since I have it at the top and at the bottom, I get to cross it off. And so my units are whatever is left over. So in this case, $394.75. Or since we asked in dollars and cents, you know that the way that you would express that is $394.75. That's all that dimensional analysis does. It's making your units apparent alongside your values. Let's try a slightly more complicated one. So if I'm 5'6" tall, how tall am I in centimeters? And I'll admit that's in good day in slightly taller shoes, but you know, around that height. And the interesting thing about this, right, I know that I have feet and inches, and I want to go to centimeters. So I have mixed units, so I better take 5'6" and unmix it, right? I could do in inches. I could start this problem in inches, and by the way, that would be 66 inches, right, because there's 60 inches in 5 feet. Or I know that there's 12 inches in a foot, so I could convert this to feet and say 5.5 feet tall, right? But I better unmix my units before I go anywhere. And it doesn't matter where you start. You could do either of those. I'm going to start with the feet because it includes 2 unit conversions, which makes this more interesting. So I start with my 5.5 feet, and I know that my goal at the end is to end up in centimeters. Well, I know that there's 2.54 centimeters in an inch. That's a conversion that I could look up, and sometimes it's given in a problem, but I know that. But I also know that feet doesn't take me quite to centimeters, so I need 2 conversions. That's okay. I can get from feet to inches. Why did I do it that way? Because I don't want feet in the problem anymore. So if I put feet on the top and feet on the bottom, it cancels. What's my conversion? I know that 1 foot has 12 inches in it, so I just fill in the numbers that I know from the conversion and put them in that order. And then again, I could look up, right? I know 1 foot equals 12 inches, and so that's how I turned it into this conversion. I also know that 1 inch is 2.54 centimeters. How am I going to line it up? Well, I want centimeters at the end, and I need to make the inches go away. So I better put the inches on the bottom so that they cancel. 1 inch, 2.54 centimeters. Feet cancel, inches cancel. I'm left with centimeters. So now I just do my math. And I find from that 167.6 centimeters. So I've gotten to the right units. By the way, this is not the right number of what's called significant figures. You can check out a later video for how that kind of thing works. But I've lined up multiple conversion factors and canceled the things I needed to cancel. Feet are gone, inches are gone, and I'm left with these centimeters that I want. And also, notice that all 3 of these numbers, 5.5, 12, and 2.54, were on the top of my fraction in my dimensional analysis problem. So I simply multiplied them all together. Now let's try a problem where we want more than 1 unit out of our answer. In this case, right, we have a container of gas. So we know something about the size of that container, the volume of that container in liters. We know something about the mass, so the amount of gas in there. And what do we want? We want the density, and they gave us units, grams per milliliter. So I know that by the time I'm done with this problem, I am going to have an answer that is in grams over milliliters. The grams are going to be on the top, the milliliters are over on the bottom. Now, you guys do remember from middle school, right, the density equals mass over volume. And we could use that, right? We could recognize that 44.01 grams is mass and 22.4 liters is volume and divide, but unit analysis can get us to the same place without ever knowing an equation. I look at this information, I notice that my problem wants grams per milliliters at the end, so that's why I put it after my equal sign to keep track of it. I notice that I have grams and I have liters. So why don't I go ahead and start the problem by putting the grams up top? Because I know that I want them up top in the final answer. And I know that I want milliliters on the bottom, so maybe we can put the liters on the bottom as well, 22.4 liters. I'm not there yet. That's okay. Let's turn liters, and I notice that liters are at the bottom in my conversion here. So liters are going to be on the top and milliliters on the bottom. And this conversion factor would be 1 liter has 1,000 milliliters. This one right here, by the way, I'm going to star it and box it and things like that. This is a conversion that you just want in your head at all times. Memorize this conversion. Don't ever forget it. You'll need it a lot. And I look at my units now. I see that the grams stayed, and they're on the top where they belong. I notice that the liters are canceled. I have 1 on the top and 1 on the bottom. And I notice that milliliters are left on the bottom right where I need them. So all my numbers are in the right place. I look at my fraction, and I see 44.01 and 1 on the top, and I see 22.4 and 1,000 on the bottom. So how would I do this math? Well, in my calculator, I'd punch in 44.01. I could do times 1 if I wanted to, but it doesn't matter, right? Divided by 22.4 times 1,000. And what's that equal to? It's this amount in grams, right? Grams are in the numerator, milliliters are in the denominator, and I get 0.00196 grams per milliliter. By the way, that's pretty normal. Gases have a low density. There's not a lot of particles packed into a lot of space. So again, multiple conversion factors. I paid attention to what stayed on the top and what stayed on the bottom. And just by keeping track of unit analysis, I don't have to use an equation. I can just line up the units where I need and the math will follow. Let's try one more. Okay, here's a much more complicated one, and this is something that dimensional analysis strategies for solving problems is really helpful for. All right, we've got this toy car company and we're making different parts in different places, and we're trying to figure out how many cars we can make, but we can't count the wheels themselves. And so when I see a big word problem like this, the first thing I can come up with by looking at it is, I don't have an equation in my head for this. There's no equation that's going to directly equate wheels of cars to pounds weighed to how many cars I can make. And so I just have to use what I know about dimensional analysis to get me out of this. And so what I'm going to start to do as I strategize is to think about the information that I have. And I'm going to start thinking about numerical things because I can kind of think about the different conversions that I could build. So I see a hopper car can contain 4,250 pounds of wheels. So if I want to think about that, maybe I could just say let's make that a different color. One hopper is 4,250 pounds of wheels. That's a conversion factor that I can use later if I need it and as I need it. I don't know how I'm going to use it yet, but I have it available. I might need to flip it around. Another piece of information that might be good to me is that a dozen wheels weighs a certain amount. So I could build myself that kind of idea, right? That 1 dozen wheels has a certain number of pounds associated with it. Last but not least, I see one more piece of numerical information, right? A dozen wheels are needed to make 3 cars. So maybe I could say 1 dozen wheels is 3 cars. What's the point of this whole problem? Well, I better look at that and say, oh, how many cars you have wheels for? So I think that cars is the operative word here. I think how many cars is what I'm really trying to get out of this answer. I think that when I'm done with all this, I will have cars. So cars is going to be on the top. So maybe what I need to do with this factor is flip it, right? Why? Cars needs to be on top. And by the way, the really lovely thing about this is multiplication and division, and it doesn't matter what order I do it in as long as I do it. So why don't I just take that one first? 3 cars has 1 dozen wheels. Oh, hey, cool. Let's now figure out this conversion factor. Look at that, a dozen wheels. I see a dozen wheels here, and I see a dozen wheels there. They match up. So why don't I go ahead and use this conversion factor? And if I look at it, I don't need to flip it, because the way that I set up my first conversion factor, if I put a dozen wheels in the numerator and the weight, the 0.0364 pounds, in the denominator, wheels cancel. Good, they weren't in my final answer, so I don't want them to be there. And now, when I look at it, I have a hopper and I have pounds of wheels. Well, it looks like pounds are in the denominator, so I'm going to need pounds in the numerator. This is another one that flips in order to work the way that I want. So 4,250 pounds is 1 hopper. What am I left with? I'm left with pounds canceling. It's really cars per hopper in my units. That makes sense. How many cars I have wheels for in 1 hopper. So I'm exactly where I need to be. I've canceled out the wheels. I've canceled out the pounds. I'm left with cars per hopper. So now, if I wanted to do my math, of course, I'd have 3 times 4,250. Why? Those are the things that were on the top of my line. Divided by 0.0364. And again, left on the units are cars per hopper. So I can do my math. 350,274.7 cars per hopper. Now, I'm not going to report that as my answer because that doesn't make sense. How can I make 0.7 cars in a hopper? Okay, that 0.7 cars isn't a full car, so I'm going to have to just round that down. What I'm going to say is 350,274 cars per hopper. So I use my intuition, I use my chemistry sense at the end of it to report an answer that truly makes sense. So to recap, right, dimensional analysis, what do I care about? I care about the value of a number. I care about the units of a number. And when I strategize to solve problems, I don't just show numbers, I show units so that I can make sure that I've gone the direction that I need to go. I can fix my work a lot easier, and I can find my problems a lot easier, and I can get to the right answer a lot easier if I do it this way.